Where did we leave off? We were trying to prove that the radius is always positive. Okay, why is the radius always positive? So I gave you a long hint. Okay, let's just do it in natural language. Right? The main idea is that the axiom points of circ tells us, this axiom tells us that there are two distinct points on any circle, which means that circle can't be a single point, which will somehow imply that a circle can't consist of a single point, i.e. have radius 0.
Would you end the same thing if you just had, instead of points of circle, you had point of circle, but you only had 1 point on the circle, and then you just had an axiom that said the radius is not 0?
Yeah, there will be other instances, there will be other applications of this axiom. For example, should I tell you one? Do you guys know if someone gives you, let's open GeoGebra. So here's a little challenge. I give you a circle, but I forgot to give you the center. If I give you just a circle, how do you find the center? With straight edge and compass. You want to take a minute and think about it? Some of you know already, but some of you don't. Take 30 seconds and think about what you would do with straight edge and compass to find the center of a circle, if it's not already there. Yeah? Think about it. Think about it. Write it down. Let me tell you what you're not allowed to do. You're not allowed to draw some line and then wiggle that line until it looks like it's about a diameter. That's not how you find a center. That's not allowed, right? That's not one of the axioms.
Like make sure the intersection point, on the intersection point of all the radiuses.
How do I draw a radius? I need to know a center to draw a radius. Make a point where?
Yeah.
Give it a second. You're telling me to draw an equilateral triangle. There's 2 points. Okay, let's say it was inside. No, second. Just the team. And then so we have one. So if you draw yeah, what's your idea? I'm gonna show you something. Do we know what?
Yeah.
Do we know that there are 2 points on the circle? That's the first thing I want. Yeah, that's why I want this axiom. Okay. So what are you drawing? Right? Yeah. Okay. What is this? How do I find that?
Have another board.
Okay, okay.
Section point.
Have you had enough? You want some more time to think about it? Some more time. Sarah, you're still working?
How should you start this?
The whole point of this, hint, start with 2 distinct points on the circle. That's why I want you to assume that there are 2 distinct points on the circle. Boom and boom. Okay, let's bring it in. Let's bring it in. So step 1. So solution. Step 1. Well, step 1 is get 2 distinct points on the circle. I mean, obviously. How does that help us? So now I have 2 distinct points on the circle. I can make a chord. Yeah, I don't even have to make in reality, I probably do have to make a chord, but GeoGebra gives us a perpendicular bisector tool, which doesn't actually exist, but you can perpendicular bisect by straight edge and compass. So step 2, which is really a bunch of steps, by straight edge and compass, perpendicular, draw the perpendicular bisector of those 2 points, or those 2 distinct points. And now what? You could, but I don't know where to get another chord, because all I've assumed is that my circle has 2 distinct points, not more. Well, you could do that, but you could also, we need some reason that that line intersects the circle, but let's say it does. So step 3, by some axiom that we might not even have yet, by some process, this line intersects the circle in 2 points, and then argue that bisect the 2 points. Where's the midpoint tool? Boom, boom. And that point G should be right on top of our original point A. Everybody see that? So step 4, find in 2 points, what are we calling these points? E and F. Step 4, the midpoint of E and F is the center. Okay, I'll let you fill in the rest of that, but does that make sense? You guys see how you would do it? Okay, so that's the idea I have foreshadowing this process, that if you're given that I want two distinct, it's not enough to have one point on a circle. You were proposing that there's one point in a circle and that the radius is always positive. How does that tell me that my circle isn't just a single point with a positive radius and a single point in the center? How do I get another point on the circle distinct from the first point? This is what makes formalization so hard. All the things that are in our natural intuition tells us is actually not justified until it's explicitly justified by the explicit axioms that we've written down. Cool? Okay. So that was a little aside, challenge question. Let's close that up. So what? Why do we even want? Okay, so we've agreed that we want two distinct points on the circle. Let's recurse back to this is where we left off. How do you show that the radius is positive? Did anyone do it? Back to the original problem of positivity of radius.
This is, you can apply the distance laws that.
Exactly. I mean, we sort of wrote it out over here, right? We know that distance is non-negative. So by distance non-neg, either the distance from A to B is equal to 0, or the distance from A to B is greater than 0. And in the latter case being what we're trying to prove. Latter case, we are done. Okay, so let's say that. Let's say that formally. So let's just say have either 0 is equal to dist AB, or 0 is less than dist AB. Now, how do we prove this? This is something about the real numbers, because we know, I mean, first of all, let's just record that, let's call it that 0 is less than or equal to dist AB. And what's the proof of that? Dist non-neg given A and B, right? So we know that the distance is non-negative. That means either the distance is 0 or the distance is strictly positive. Now that's just a statement about the real numbers, which means it's not a statement that we coded up, which means it's a statement that's somewhere in the math library of Lean. And it's probably a one-line result in the library. And come on, I shouldn't have to know the name of this. So let's try to find it. It's got to be something like, so I'll do by and exact, and I don't know what exact will be. So I'll do exact question mark. And exact question mark says, oh, try this. I think it's called decidable dot equal or less than of LE this. Okay, so this exact question mark finds the theorem in the library. And you just click it right there and it solves things for you. Okay, so again, that was a little bit of black magic, right? Yeah. Okay, so formally, first let's record this, and then we want to prove this, and this is a basic statement about the real numbers, not something about geometry, So it's not something that we have control over. We didn't code this up. So the name for the theorem that closes this goal, is not known to us. But it's something so basic, it's got to be in the library. But it's such a basic fact that it must be somewhere in the Lean library, mathlib library. the way to search for something, if you think it's exactly, if there should be a theorem, the way to search for a theorem that you suspect is exactly something already in the library is to write exact question mark. When you do that, the if it manages to find it, I mean, if I tried it for let's try it here by, whoops, I need to have the by not inside the comment. If I tried here and I say exact question mark, oh, it's smarter than I thought. That's true. Okay, but what if I said distance is greater than 1? There's no justification for distance being greater than 1. I say exact question mark, and it says, give it a second. No, I couldn't, I couldn't close the goal. I couldn't figure it out.
So if you say exact question mark, it basically helps you with the next step of the code or what you need to put in that.
So the way exact question mark works is if it can solve the goal immediately, it's going to look through all the theorems that it knows. Apparently, I didn't know that it would know the theorems that we defined, the axioms that we defined, but it does know the axioms that we defined. And it says, yeah, what you're trying to do is prove by this non-net. So if you can find exactly a one-line solution, it does it.
But like, what if it's more than 2 steps? Does it not do?
Right. It often doesn't, it sometimes goes like a little bit more than 1 step, but there could be a one-line proof. I mean, in some sense, every proof is a one-line proof just with a long enough line.
So when did you get the thing that says like it's less than or?
Yeah. So let's look at it again. I'm just gonna revert this back to dis non-neg AB, and then I did an exact question mark. And it said, try this, and it says a whole bunch of things, decidable dot eq or LT of LE. You're either equal or you're strictly less than of less than or equal to. And what's the less than or equal to? This. The previous thing that we didn't give a name is called this. So that's why it says, that code will solve it.
So since we didn't give it a name, it just saying this.
Well, we didn't give the previous thing a name. We could call this Sanvi, and then it would say you close it with Sanvi.
Oh, okay.
It's this statement that it's referring to. Okay, so that's why it's suggesting this. We didn't name it, so it's saying this. But it found the name of the theorem for us. The goal state. When you do that, if that theorem already exists, you'll see in the goal state something like what we just saw. Try this. And when you click on the exact, it replaces your text with the text that solves the goal. Okay, so here we go. I'm about to click this text. Instead of an exact question mark, I'm going to click there and it'll say exact, decidable, yada, yada. Here I go. Boom. Exact decidable. Okay. Auto completes it for us. All right. So far, so good. Done. Next step. We have to break it into cases depending on whether we know that either the distance is 0 or the distance is strictly positive. We have to break it into cases.
Use constructor, please, or no?
So this is not a constructor. Constructor is if the goal is an and of two things.
Oh.
This is
not
a goal and it's an or.
It's an or and it's an hypothesis. So if you know that either something is true or something else is true, and you want to break it up by cases depending on which of these cases is true, you want to continue the proof depending on which case is true. So let's just record that. We now have a hypothesis that's called this. Should I give it a name so that it's not this? Yes? Ian, what name should we give it?
Any options?
The world is your oyster. Oyster. Okay, this is called, what do you?
Vinay.
You're gonna mess with Vinay? Y or I? I?
Yeah.
Y. Okay, that's what I thought. Okay. So we have, I will leave it this in the official notes if that's okay with you. We have this hypothesis. Bless you. We can't use constructor. Can't use constructor because first of all, it's not in the goal, not in the goal. And second of all, it's not an and. How do I get an and symbol? It's not an and. So this is an or, and it's in the hypotheses. We want to break the logic, the continuing logic, by cases, according to which is it, which case it is. So that's called. Any guesses what that tactic is called? If you want to break something by cases, it's called by cases.
Oh,
That's called by cases. That's called by cases. So we do by cases. Yes.
so basically like constructor is for goals. If we do by cases, it breaks apart the goal like statements.
Well, let's think about this logically. Okay. More generally, if we have a hypothesis H that either P or Q is true, where's my or? Oh yeah, do we know that this thing means or? Yeah, okay. Either P or Q is true, and you want to continue with the proof, then more generally, if we have a hypothesis H, then writing by cases H results in, so let's try this, by cases Binet in our case. What's the matter with Binet? Oh, I have to give it with HH, using HH. I forgot what don't understand.
You change this to the previous one.
You mean here, by cases this? Yeah, I forgot how to use using HH with HH. Oh, is it not by cases? It's cases. It's cases. By cases is something else. By cases is when you yeah, it's cases this with HH. Oh, come on. Where's my little helper? Where's Copilot when I need it? Copilot, lean 4. Go. Case is this. Oh, that's what I wanted. Come back. There it is. Generate a pattern. There we go. Okay. It shouldn't be this complicated. So it is with.
It wants a proof for why.
It wants a proof for if it's the left side or the right side. I thought it was just cases with HH, but no, it's not letting me HH. All right, so here's what happens. When you write cases this, let me turn Copilot off. It's not Copilot that I want. It's this little light bulb. The light bulb, if you click on the light bulb, it says generate a pattern match. And now we can see what the two cases are. One case is, let's call this H. Instead of H, let's call this dist equal. Dist eq, and the other case is dist not eq, not eq. So let's look at the second case first. Okay, this is the P and the Q. The Q is that the distance is strictly positive. And what are we trying to prove? Which is called. This is what this not equal to Q is what this hypothesis is called. What are we trying to prove?
Things we have to do.
The same exact thing. So exact this not equal. We'll solve that goal. So instead of a sorry here, I'll just say exact dist not eq. Okay. How about the other one? So this is the one where we have to actually do some work. So instead of a sorry, let's get into it. Okay, so the syntax, let's just record the syntax. Sanvi.
What is that?
I and L, so there's a nicer way to break this up, and I just don't remember what it is off the top of my head. And what I would do is ask an LLM what the right syntax is. But instead, we're going to follow the sort of proper lean syntax, which is cases this, it says we're going to break up into the two cases. And then INL versus, so this is like I don't know what IN stands for, but L is the left-hand side and R is the right-hand side. Yeah, in the left case and in the right case.
So the purpose of it is it's just like breaking apart so we can just read easily.
Right, so look at the goal state here. Our original goal state was we're trying to prove that the distance is strictly positive. And we know this, that either distance is equal to 0 or the distance is strictly positive.
Yes.
So if I go into the left case, now I assume that the distance is equal to 0. And let's see if we can prove that the distance is strictly positive.
Okay, but if you go to the right,
And if I go to the right one, then I know that the distance is strictly positive. I'm trying to prove the distance is strictly positive.
yeah.
And of course, that's just exact. So let's go into this case. This case says we know that the distance is exactly equal to 0, and we want to show that the distance is strictly positive. Now, how do we show that the distance is strictly positive if we know that it's exactly equal to 0? We can't. It's not true. That means we must have stumbled into, either we made a mistake and we can't complete the proof, or we can complete the proof, we've just stumbled into a situation that's not possible. And if we, so let me record all of this. Writing cases, okay, so it's a little more complicated. Writing this, I'll just copy the whole thing and hopefully you'll figure out how we got here. Well, okay, then writing splits the goal into two goals. One assuming that P is true, and another assuming that Q is true. Okay, in our case, Q is exactly the original goal. So this line exact solves everything. We need to see what happens in case P, where the game board says what? So what does the game board look like now? Right there, the game board says the distance from A to B is equal to 0. And we're trying to prove that the distance is always strictly positive. Okay? So we're obviously in a state of contradiction. So here's the magical thing. If you're in any situation and you can prove false, then you can prove anything. We must be in a situation that proves false. If we can prove false, then we can prove whatever we want. We must have stumbled into a well, I already said into a contradiction. So there's a tactic to replace, yeah?
We're essentially trying to prove that 0 will actually never equal its AB, so we'll never have this case to begin with. Right?
That's right. That's exactly right.
We're trying to prove that this AB will never be 0.
Exactly right.
because the circle can't have a radius of 0.
Exactly right. note, we're trying to prove, let's recall that we're trying to prove that the radius is always positive. So this is the part of the argument that says if the radius is 0, then we get a contradiction. This is the part of the argument that says the radius can't be 0. Okay, does that make sense? Exactly as Khalil said. So where are we going to get our, once you know that what you're trying to prove is not true, you just replace it by false. To replace any goal by false, the tactic is called, that's a good guess. That is a good guess. I don't know a good way to tell you what it's going to be called. It's called ex falso. Ex falso is like, what's that? Avada, not Avada Kedavra. Like Expelliarmus. Like Expelliarmus. I don't care what goal you're trying to solve. If I can solve false, then I can solve any goal. So ex falso I think of as Expelliarmus for goals.
Probably means false.
Out of falsehood comes anything. Exactly. From false, I can prove anything. Okay, so we've changed the goal to false. The goal now says, can we prove that we're in a state of contradiction? All right, so let's look back at our natural language discussion. If it's the second case, then we're done. We just need to rule out the first case. So where was that? Well, that happened actually right here. This is the second case, and in the second case, we're exactly done. Now we're arguing by contradiction. We want to prove false. So that's where we are here. And what's the idea? Sorry, please.
So if we finish with ex falso, why do we still use
Oh,
Sorry.
we have to prove false. We
Oh,
can't get through the turnstile until we prove false.
oh, so it's still proven.
Yeah, without that sorry, it'll just give me an error that says, hey, you're supposed to prove me false and you haven't done it yet. So sorry says, yes, I know I haven't done it yet. Please don't give me the error message. By the way, now it's giving me an error message down here because there's no more goals to be solved. So I can take off that sorry. Okay. So let's remember the idea. Using points of circ, we get 2 distinct points on the circle. Cliff?
We do have points of circ. Alpha.
Alpha, beautiful. So have points of circ alpha says that there exist all of these things.
You obtain E at E on alpha.
Love it.
On alpha, E is not equal to F.
And we obtain that from
From this.
this. Everybody see that? You guys are really getting the hang of this. Okay, so let me record this. Okay. All right, so we've got now 3 points on the circle, B, E, and F. We got the center A. We know the distance from A to B is 0. So what's the difference from A to E? 0. And what's the distance from A to F? Okay. So since distance from A to B equals 0, then A equals B. Where do we get that from? This positive F. So let's see if we can find that. So let's call this have A equal B is the fact that A is equal to B. And let's start the proof of that fact.
Yeah, you can say this one's fine. Yeah, we're interested.
It will. So let's look at dist pos def AB. It says that the distance from A to B is 0 if and only if A is equal to B. So which direction do we want? Dot 2, we want the dot 2 direction. We want the dot 2 direction. Are you sure we want the dot 2 direction?
That's not one.
The dot 2 direction is if A equals B, it's the other way around. It's the dot 1 direction, which says if AB equals 0, then A equals B. Does AB equal 0? Where do we know that from? We're assuming it from dist eq. So I'm going to feed into it dist eq. Will it work? It does not work. The reason it doesn't work is this e is 0 is equal to this AB. And what it wants is this AB is equal to 0. Dot sim. Dot sim. Ah, and now we have exactly the thing that we wanted. Whoops. Exactly the thing that we wanted. So actually I can just delete all of this, the by and the have and the sorry, and that is the proof. Okay, so the fact that A is equal to B is proved by this positive F, AB. Dot 1 is the forward direction. We fed it this E sim. Every single T has been crossed and every I has been dotted perfectly, or else the computer will not be happy. Okay, does that make sense? Okay, so we have that A is equal to B. What else? How do we get that the distance between A and E is also 0? The definition of the circle. Yeah, so we did this part. We did this part. And now let's do this part. But points on circ if and only if says that the radii are well defined. So what should we, let's just do point on circ if and only if. Okay, what does it want? 3 points. So which 3 points? It wants A to be the center. Do we have a center? A. We want B to be a point on the circle. B is a point on the circle. And what point? Let's compare it to E with respect to what circle? Alpha. Okay, do we know that A is the center of the circle?
Yes.
Yes, A cent of alpha. A cent of alpha. Do we know that B is on alpha? B on alpha. You guys are really getting the hang of this, right? Now we have an if and only if. Which direction do we want? Do we know that E is on alpha?
Yes.
So we want the forward direction, 0.1. Yes.
You don't say 0.1, I'll just assume that you're going forward direction.
No. No, if I don't say 0.1, it's an if and only if. And if I try to feed it, E is on alpha, it'll say, I don't know what you're talking about. 1 is an if and only if, and now you're trying to feed me something. But I have 2 directions. So it's only when we convert it into the forward direction that it eats something, and the thing that it eats is this. Okay, this to E equals this to AB. Okay. Do we know about the transitivity of the equal sign?
Yes.
Yes, we talked about this. So if I have this thing and I do dot trans, well, if X is equal to Y, and this needs to be the other way around, this AB needs to be equal to 0.
Oh, geez.
So that's dot sims. So let's try to build that up. Let's start with this dot trans, the transitivity of the equal sign, with dist eq dot sim.
That's fine. About 7 doctrines.
Okay, dot trans, I'm not recording the things that I'm saying. We did a bunch of stuff. Well, I'm video recording, so hopefully you'll be able to watch the video. I won't write it down right now. If you have H1 is that X is equal to Y, and H2 is that Y is equal to Z, then if I say have H3 colon equals H1 dot trans H2, so that's the property of the transitivity property of the equal sign, means I can zipper these two together.
And X is equal to.
This will have type X is equal to Z. Okay, does that make sense? So, so the trans is zippering together what used to be this, that these two distances zipper equal,
Yeah.
and it's gonna apply transitivity to this, but symmetry. So that the dist AB and the dist AB are eaten, and all I get is the dist AE is equal to 0. Okay, I think we're actually going to finish a proof today. Like we've been recursing proofs, but yeah, Jeremiah likes that. All right, so that's dist AE equals 0, and now how do I get the fact that that means that A is equal to E? Yeah, let's have A is equal to E, which is A is equal to E, and the reason is dist pos def. Yeah, dist pos def AE, I guess, dot 1, and then this. Everybody see that? Okay. You want to see what that was? Let's build it up piece by piece. So we have dist pos def AE. That's that the distance between AE is 0 if and only if A is equal to E. The dot 1 is the forward direction. Dot 1 is the forward direction. Do I know that this AE is equal to 0? That was the previous this. And now we know that A is equal to E. And so that's what this line is doing. I just gave it a name, and I said, here's what it says. It says that A is equal to E. Okay.
That part, like you need that part where you're telling them what it says, or is that essentially just an amazing?
That's for us.
Okay,
Yeah. It knows what
it knows what it's proving.
what it's proving.
That's for us to know what that might prove.
That's right. Okay. So we've shown that the A is equal to E. Can we show that B is equal to E? I mean, it doesn't matter. We don't have to show that B is equal to E. What we're really trying to show is that E is equal to F. So how do we get A to equal F? It's the same exact argument. So I'm going to write, I'm just going to copy and paste all of this stuff and just change every E with an F and an F. And A is equal to F, and A is equal to F, and A is equal to F. I mean, E is equal to F. Okay, so now we know that A is equal to E, and we know that A is equal to F. Here's your challenge. Take 30 seconds and write down what line of code will get us F E is equal to F. E is equal to F. So I'll say have E eq F is the fact that E is equal to F. And how do you prove that? How do you piece together the fact that A is equal to E and that A is equal to F? It's ever so slightly tricky. I mean, it's not tricky. Some of you have written it down already. Talk amongst yourselves.
You have minutes, so.
Did I lose you? How long ago? An hour ago?
What is this?
It's definitely a trans. It's the trans of these two things. Except.
I'm gonna second me.
And what we're about to prove is that in both.
And because I have A is equal to E.
I have A equal to that.
I want this guy. That will give me. But how do I get this thing back? This world.
Yeah.
It's what property V are. I can't imagine that. The big stop sim. I'm seeing that. Not friends. And so what am I gonna? For that?
Oh, because.
I was looking
No, I was gonna say, it's that matter.
You can use it practically anyway, so like, I can just, it's gonna stay on high. Alright, we'll try to do that. I might be able to find it, stuff like that. Also, like this. We have a turnstile. We haven't had it. Sorry says I'm gonna hop over it without getting a ticket.
So, like, what prevents me?
You can put a sorry for everything, you'll have a. It will work, but it will say your code is okay because you use sorry.
Yeah, sorry, and sometimes it's just like, oh yeah, I'm gonna prove this later. So, I mean, you could write sorry at the very beginning of, you could say, here's my theorem, I wanna prove it by sorry, and then you just be done. Got it, like, it's really just a placeholder to get rid of the bugs showing up, like.
Yeah, the error messages.
And-
Did everybody get it? So what'd you write? Other than Sanvi. Navia, did you get it? Sayuri, did you get it? I think you got it. A equals E dot sim dot trans A equals F. Great job. Great job. That does it. So here's a question. Will the library search find it? So I'll say by exact question mark. And it couldn't find it. It couldn't find it. Sorry. Because it's 2 steps.
Oh, maybe one step.
It should be able to do 1 step. I'm curious. So what are we trying to prove here? We're trying to prove that dist AF equals 0. So let me tell it what the statement is. Dist AF equals 0. And now I'll comment this out and I'll try exact question mark. Does that find it? It does. But its proof is really, I mean, yes, this works, but come on, that shouldn't be the proof. It's inefficient. It's like it found all kinds of crazy theorems that when you chain together, equals 0, if and only if an additive semi-conjugate by, I mean, this is nonsense. So it closed it, but it didn't close it nicely. We're going to close it nicely and we'll close this. So this one, it didn't even close. We needed Sayuri for that. Okay. So now we know that E is equal to F. And we're trying to prove false. And we also know that E is not equal to F. How do we get false out of that? Yes. Remember that, what's it called? E not equal to F. So, yeah, again, I haven't kept track of what we said, but in the interest of proving a theorem, I won't write it all down. We've gotten to the point where we proved E equals F and E is not equal to F. I need that little, and E is not equal to F. Recall that the latter, this E not equals F, is by definition E equals F implies, give me an arrow. Thank you. Implies false. 2 things, E does not equal F by definition means if you can prove equals F, then you can prove false. But we proved equals F. So this thing is waiting for a proof of E equals F. If I feed that in, I'll get false. Everybody see that? So if I feed in E is equal to F into E is not equal to F, we have proved false. And so this thing is exactly the thing that we need to close our goal. So instead of having it, we can just say exact. And now sorry is no longer needs to be there. So let me record, well, I'll just put all of this stuff here. Guys, we proved a theorem. We finished them. I know fake applause when I hear it. Okay, here's your homework. Here's your homework. Go, I'm gonna write all of this, I'm gonna put all of this code in this main file. Thank you. I'm gonna put all of this code in the main file. Your homework, should you choose to accept it, is to try to complete the proof of circ of in center.
Fix that one. So points.
We also have to fix that one use of yeah. But we now have all the information we need. We know that dist of AA is 0. We're trying to prove that dist of AB is we know that dist of AB is positive from that theorem. So finish the proof. Homework is yeah. Well, now it really is. Now it's homework that you can do. Before it was homework that I wanted you to think about and struggle with and find where the missing axiom is. Now we've added the axiom, we've added that API lemma that radii are positive, and you can finish this circ of center. So homework, circ of center.